We finally reached the moment we've all been waiting for. What is the limit? It's time to formally define it and make it precise. We've been using words like close to X and arbitrarily close to L. But what does that mean? How close is close enough? What does it mean to be infinitesimally close to L? And what does it mean to be close to A? When we're looking at these, we have to make these mathematically precise in order to have a true definition. This true definition is called the epsilon delta definition of a limit. Now, keep in mind, calculus was created in the late 1680s, early 1690s. It wasn't until the late 1800s that Augustin Cauchy finally figured out how to prove it mathematically, to make it mathematically precise. It took a really, really long time, nearly 200 years. This is a difficult topic, probably one of the most difficult, if not the most difficult, in the course. I've written a template for you to use to help you structure these proofs. All your proofs will take the same format. When you write a proof, it reads like a paragraph. So we do use punctuation like commas and periods. But we also use mathematics, and the mathematics is part of the paragraph. Let me share my screen with you and we'll get started. Here are the learning objectives that we're going to cover today. Describe the epsilon delta definition of a limit, and epsilon and delta are just Greek letters, like X and A are English letters. When we're looking at the second one, it says we're going to apply this epsilon delta definition to find the limit of a function. Now, we've been finding the limit of a function, but we haven't actually justified why what we're doing works. We need to do that now. So we'll also use the epsilon delta definition to prove the limit laws that we learned in section 3. We're also going to use the epsilon delta definition to prove some one-sided limits and infinite limits where the y value is going to infinity. But before we can get to the actual definition, we need to talk a little bit about closeness and a few things about the absolute value notation so that you're prepared when we get to the definition. Let's start with how close is close. We need to define what we mean by letting X get close to A, but not to A, and by letting the function y value get close to L. What does close really mean? If we take the statement f of x minus L and we put it into absolute values, then we're really talking about the distance between a y value on a function and the L value. If we say it's less than epsilon, then we mean that the distance between the y value on the function, let's say right here, this is my f of x, and the distance that is from L, which is right here, has to be smaller than some epsilon value. So let's say that we take the distance between them, and we know this distance between them has to be less than epsilon. However, depending on the graph, we don't really know if L is going to be above the y value or below the y value. It could be in either direction. So f of x minus L could be positive, or as in this case, it could be negative. To force it to represent the distance, we take the absolute value. And we say it's going to be less than epsilon. Epsilon is a value we're going to choose, and it's totally arbitrary, but it's going to be small. We want to be very close to L, so we'll choose 0.1, 0.01, etc. The trick is, no matter what I choose for epsilon, I should be able to figure out how close I need to be to A to make that happen. Now let's look at this next statement down here. 0 less than the absolute value of x minus A less than delta. This is the Greek letter delta, the lowercase letter. Again, when we write this, we mean that we have some a value. And on our graph, I'll put a down here. It's on the x-axis, right? And x can be somewhere around a, not at a, but around a. Maybe the function is defined there, but maybe it's not. Maybe it's a whole or a displaced point where the limit still exists, but the function does not. When we're looking at this, we want to know how far away from the a I could be so that my f of x is within epsilon of L. So when I'm looking at this particular one right here, I can tell that my epsilon would have to be pretty large. If I come up, I'm going to make this one a little tighter. This would be this value here, and this end of the interval would be this value here. So in order for my function value to be close enough to L, I would have to set epsilon to be half of this distance right here. Otherwise, it's not close enough. So let's take a look at what this means. Again, I don't know if I'm on the left side of A, so x minus A is negative, or on the right side of A, so x minus A is positive. To force it to represent the distance only, I take the absolute value. That means magnitude or distance. The distance between x and A is greater than 0. What does that tell us? Well, it tells us they're not equal, which is the idea of the limit. You get very close to A, but you never actually get there. This means that x cannot equal A. Now, if it's less than delta, what is this delta? Delta is the distance you can go out from A on either side. So this interval that I've drawn here is 2 delta if I go the same distance on both sides. So delta's got to be how close to A on either side I need to be so that the function value will land within an epsilon distance of L. Now, let's talk about the meaning of absolute value in the formal definition. When we write something in absolute value, what we mean is that if it is less than a number, a positive number, then that means that this thing in the absolute value actually sits between epsilon and negative epsilon. In other words, if I want to write the absolute value of f of x minus L is less than epsilon, which looks kind of like a, I don't know, a cursive E. When I look at this, I could also write that this means that f of x minus L without the absolute values has to be between epsilon and negative epsilon. Well, that makes sense. Think of it as distance. Let's pretend this is distance and epsilon is 5. We'll take something ginormous for epsilon. If the distance is less than 5, then I could be 5 steps to the left, or I could be 5 steps to the right. 5 steps to the left is negative 5. 5 steps to the right is positive 5. That means I'd be between negative 5 and 5. That means the inside of the absolute value would be between those two values. The next thing I can do, of course, is go ahead and isolate the y value of the function f of x by adding L to all 3 parts of this compound inequality. So I'm going to add L to all 3 parts. And this gives me the statement that you see here. L minus epsilon has to be smaller than the function value, which is smaller than epsilon plus L. So when I'm looking at this, if I come back to my graph up here, L minus epsilon could be down here, L minus epsilon, and L plus epsilon could be up here. Then all the function values that fit close to A will land the y value in that range. We have to be able to find a delta, how far from A I need to be, that forces that to happen no matter what I choose for epsilon. If it doesn't depend on what I choose for epsilon, meaning I can always find a delta that will work for any epsilon, then the limit exists. Now let's take a look at the next statement. The statement here again means absolute value of x minus a greater than 0 means x is not equal to a. Having x minus a absolute value less than delta means the distance between x and a is less than some number delta. Let's say it's 3. That means that x minus a has to be sandwiched between 3 and -3. And then, of course, I can isolate the x value by adding a to all 3 parts. And when I add a to all 3 parts, I get that x has to be between a minus delta and a plus delta. Let's take a look at the picture here, which is better than my hand-drawn picture. I have a curve, f of x, which is here. I want to know how close I need to be to a so that all the function values land within L minus epsilon and L plus epsilon. I choose epsilon first. It's totally arbitrary. I choose what I want, but small usually. And then I go hunting for delta. If I've chosen epsilon to be this distance here and this distance here, that means that this distance is actually 2 epsilon. I could be epsilon away above or epsilon away below. I want to know what delta I need to choose to make that happen. So the thing I do with a graph is I come over and hit the graph, and then I come straight down to the graph. What does this mean? Well, let's come over from another point that is not within epsilon of L. Do you see this point here? It is further away from A. In order to get any value between a minus delta and a plus delta to create a function value within epsilon of L, I need to make sure that all the values in the yellow gold band have y values that fit in the blue band for the y value. Now I'm going to take the lower one and come across. This is my other band for the epsilon I chose, and it's here. Now, sometimes, because of the function shape, the distance between these is not the same. In fact, that's the norm, that the distance on the left side and the distance on the right side of A may not be the same. What do? We take the smaller one and let that be delta. Whatever the smaller one is, I can always go smaller. In this case, they're the same, but that's because this is one created by the textbook to teach you the concept. That's not normal. If this delta range works, so that this is delta here on the left, and this is delta here on the right, and the distance there is 2 delta, then anything I choose that's smaller than that would also work. I don't have to choose that delta. I could take half of that delta. If I take half of the delta, and I'm running out of space, so let me clear some of this out. Let's say I go from here to here. Trace these y values. And notice that they're still landing within the blue band. I can always choose a smaller delta. If the larger delta works to make the function within epsilon of L, then I can always choose a smaller delta. As the x values get closer and closer to A, the y values get closer to L. If you look at the graph down here, in each picture, they've taken delta and shrunk it. So they've made it smaller in each case. Here, delta is about this wide. And then they took about 2/3 of it. And then they took about 1/3 of the original delta size. As they shrink that, notice that the y values from the edge of our 2 delta interval become closer to the value of L, but they all fit within L minus epsilon and L plus epsilon. In other words, you can always take a smaller delta if a larger one works. If epsilon gets smaller, then delta will have to get smaller too. If, for example, I find that a value of 0.5 works for delta for an epsilon value of 0.1, but then I choose to make epsilon 0.05, then delta will no longer be able to be 0.5. It's going to have to get smaller. Most of the time, however, because it depends on the epsilon we choose, the value of delta depends on epsilon. So most of the time, we choose a number for epsilon, and delta becomes a multiple of epsilon, or the square root of epsilon, or epsilon squared. In other words, it could be half of epsilon, double epsilon, epsilon squared, square root of epsilon divided by 4, something like that. Let's now go ahead and define it. We've been waiting a long time for this, and it is a difficult concept, so take a pause. If you're tired, you may want to wait until you're more awake. This is a hard concept. Here's the statement of the limit that August and Cauchy developed. Let a function, f of x, be defined for all values of x except a over an open interval containing a. What does that mean? We have a function, we have an a, and we know that the function is defined over some interval like that at every point, except we don't know what happens at a. So I put a question mark. Let L be a real number. Okay? The real number L represents the limit as x approaches a, which is going to be right here where the question mark is. Then we say the limit as x approaches a of the function equals L if for any and every epsilon I choose, epsilon's a distance, so it's always positive, I can find there exists a delta, another distance, greater than 0, such that as long as x is not a, greater than 0, and the distance between x and a is smaller than this delta, then the function value will be within epsilon distance of L. This is the meaning of the limit, the precise definition. Now let's take a look at our picture right here, and let's arbitrarily set an L value and an epsilon value. I'm going to choose epsilon to be that wide. This interval right here is 2 epsilon. It's going to be L plus epsilon and L minus epsilon. Now I want to know how close to A I have to be. Epsilon is chosen from the beginning, it's fixed. You cannot affect it. You cannot affect the value of A. It's fixed. You cannot affect the value of L. It's the limit, what the function looks like it's going to hit as it approaches A from both sides. You can't pick the function. The only thing you have control of is delta. I'm going to take each of these y values and I'm going to draw across to hit the function. In this case, I can see that it hits here and here. Now I pull those down to the x-axis to find the interval over which all those values will fit within the range. Notice that I've got a shorter interval here on the right than I have over here on the left. The one on the left is definitely longer. Now, I cannot choose that value to be delta because it's longer. If I chose a value over here to the right of the original interval, it won't fit within that value. So what I'm going to say is I'm going to choose this part right here, the smaller of my two distances, to be delta. I can always go smaller for delta. And now I know that if I fit between here and here, all my function values land between L minus epsilon and L plus epsilon. Let's break down each of the phrases and translate it into words. The definition is, for every epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than the absolute value of x minus a, which is less than delta, then the absolute value of f of x minus L is less than epsilon. Very stylized, very formal writing. Let's translate into normal English. If for every epsilon greater than 0, for every positive distance that I choose, epsilon from L, there exists a delta greater than 0. There is a positive distance delta from A. Epsilon is how far from L, y values. Delta is how far from A, x values. Such that if 0 is less than equal to x minus a less than delta, if x is closer than delta to a and not equal to a, then f of x minus L in absolute value is less than epsilon. Then f of x is closer than epsilon to L. The distance between f of x and L is less than epsilon. I want to compare this to the childhood game Battleship. I had a hard time when I first started teaching explaining this concept to students, and students really struggled. So I came up with this analogy with Battleship, and I hope that it will help you to understand a little bit what we're doing. We're going to visualize that we're on a destroyer on the ocean, and we are chasing a battleship. We are trying to sink the battleship. So we are going to fire missiles and try to sink it. Now, in order to sink the battleship, we have to hit the battleship. The best place, of course, would be to hit it in the center. So the center is going to be our L, our limit value. We're going to let epsilon be the distance from the center of the battleship to the front of the battleship, and from the center of the battleship to the back. Whichever one is smaller becomes epsilon. We need the missile to hit the boat. Now, we want to fire those, so we're going to choose that epsilon to be less than the distance from the middle to the front and the middle to the stern. We can't change our launcher once we're on the ocean, and we're trying to stretch things here. We're going to assume that our missile launcher always fires at the same angle and with the same velocity. We're going to think that we're in firing position. Our current location is A. if we're at A, should I move the launcher on the boat, or should I move the boat forward or back to be close enough to sink the battleship? I'm close to the battleship, but I don't know if I'm in the firing range yet. So we can think of delta is how far away from our current position I need to be so that when I fire the missile, it hits the battleship somewhere on the battleship. If we're too close, it will go over the battleship and land in the water in front of the ship. If we're too far away, it will land too short and still go in the water behind the battleship. So our error that we're looking at for hitting the battleship is epsilon, and how we have to position ourselves to be in that firing range, that's our delta. And you can see a picture of a destroyer and a battleship here. Again, what we're trying to do is once this epsilon is chosen and fixed, not moving, find the delta that forces all function values in that interval to land somewhere in there. In other words, every single x value in that interval has to have a y value that fits in this interval. Okay. Let's go ahead and take a look at a couple of applets that demonstrate this particular concept. There are two of them that I have, and I want to open them up for you now. The first applet is one written by David Badler, and it's looking at the function square root of x minus 1. So it's a square root function looking like this, and it's been shifted 1 to the right. We can see the function down here. Inside the applet, you want to make sure that you have epsilon checked, and you want to make sure that you have delta checked. What we're going to do, we can change the value of A, which is the dot down here in red. Let's change our value of A. I've put A now somewhere between 8 and 9, roughly at 8.5. Okay? If that's my A value, I have a problem. Notice now that my values are not landing within this epsilon range of the limit. So what I need to do is I need to change my delta value. So I can come over here and I can change my delta values. Epsilon is set to be 0.6. I can't change that. That's just what it is. Let's see if I can shrink my delta. Oops, my x naught is in the wrong place. Let me move my x naught over here. Now, where is my x naught controller? Okay, here's the value, test value of x. Let's see if we can shrink this purple band, blue band that you see here, so that all the values for y fit inside the yellow band around L. I can't change epsilon. It's fixed. Notice that right now, part of this range does land within the band and it's green. However, part of this blue interval around my 8.5 is landing outside of here and it's red. Let's keep shrinking the value of delta. Ooh, can I even do it? I can't. What does that tell you? That it's not working. I'd have to practically go to 0. Unfortunately, this one doesn't go small enough. Let's try widening our epsilon. See if we can get it to fit. Now I can do it. This delta works, that delta works, that delta works, that delta works, but that delta does not. Did you see that little bit of red popping up in here? This means that if I'm going to be close enough, I've got to make sure that this distance is less than where I am now. I can always take a delta that's smaller and they'll all fit still within the band around L. All right. The next thing we want to do, I think I've got the points backwards. I think X naught is A. And this is just telling you what the value is at a particular point. So boom, right there, I can start my interval. And over here to here, keep going, keep going. I can really have it wide on this side, down right there where it goes red. All right, so in this particular one, X naught is A. Let's take a look at the other applet. I'm going to make my screen a little bit bigger, see if it will blow up some. This one is created by Chuedong Fan Yamada, someone that I've worked with who's published in the journal I'm editor for. And she has many, many different applets for concepts in calculus and other classes as well. So when we're looking at her particular one, she's looking at a different function. I can't remember exactly what her function is. I think it says somewhere. I don't see it. Okay. All right. So when we're looking at this over here, what we want to do, and I'm going to pull this, if I can pull it up. There we go. So it's centered a little bit more. Pull this over. She has the definition for the limit up here. You want to see the point, and she's labeled hers A, which is helpful. And you can see an A minus delta and an A plus delta. This yellow band is the interval around A set by delta, the delta we're looking for. Epsilon is chosen first. Epsilon right now is 0.25. The trick is I've got to make sure that when I choose epsilon to be 0.25 from L, that every y value between A minus delta and A plus delta fits inside the blue band around L. And right now, they do not. That means my delta needs to get smaller. And I'm afraid mine can't get smaller. I think I've gone as small as like, oh, wrong way. Let's keep going. Think about when you think it might be outside the interval. I'm getting close on one side. If you look at this one right here, notice on the right side, it is touching the edge of the graph and the edge of the blue band. I can't go wider on the right side. This is the maximum delta that I can use for the value epsilon is 0.25. I can choose a delta of 0.25. It can get smaller, but it can't get bigger. Even though on the left side, I still have some space inside the blue band, I don't on the right. I have to choose the smaller of the two distances. You can practice using this if you want with different functions. You can see now the function down here. So you can put in different functions, which may help you when you're trying to find the value of epsilon on the homework. Let's now come back and go through the template that I've created to help you learn how to write the epsilon delta proof. Remember that this is very stylized, formal mathematics proof writing. It is not meant to be just mathematics. There are words inside of this. It reads like a paragraph, but part of the paragraph instead of words is mathematics. We're going to divide it into two parts. On the left side, we'll eventually write the formal proof. The right side will be what we call our scratch work, but the true work occurs on the scratch work side. Now, don't leave it off because your professor probably wants to see both sides. So on the scratch work side, we actually start with the conclusion we hope to prove, that f of x minus L in absolute value is less than epsilon. That's not what we actually do in the formal proof, but in the scratch work, we start with the conclusion and work our way backwards to find the right delta. Then we rewrite the proof going in reverse order to the scratch side, starting with the value of delta and showing that that proves that f of x minus L is less than epsilon away. At the very end, we write QED, which is Latin for quo erat demonstrandum, which means that which has been shown or that which has been demonstrated. Or in grad school, quite enough, I'll let you finish it. All right, let's take a look at my template. It's a full page template, and I've got writing in purple to show you directions of things you might want to do. I've highlighted the blanks where you fill in things, and then I have written in black the stuff that is going to be in every one of your proofs. It's not going to change. Now, what we want to do is we start with the statement we're trying to prove. Prove the limit as x goes to a of f of x equals L. I take this number for L and I write it right here in this blank. Then I do some arithmetic or algebra on what's inside of this absolute value. I might factor it if it's a fraction and try to reduce it. I might factor out a constant. I might take the square root of both sides. I might square both sides. I apply some kind of algebraic rules so that when I'm done, I end up with x minus a less than something. That's my goal. My goal at the bottom is to have x minus a, what the value is getting close to in the limit, less than something. And the something probably has epsilon in it. Then I start the formal side. Once I have this, I'm ready to actually write the proof. I start with the way the proof reads. Let f of x equal, write the function from the limit here. Put a period, or not yet, and let epsilon be positive. Then put the period. Choose 0 less than delta equals whatever you found down here goes right here, such that if 0 is less than x minus a, take your a from the limit and put it here, less than delta, comma, like I've got 2 commas, then, and then the next thing you're going to do is you're going to write the second to last step here goes first. The one above that goes second. You're going to repeat these steps here until you finish with this one at the bottom. So it goes in reverse order. That is the thing we're trying to prove. And then we finish the proof by stating the limit as x approaches a of f of x equals L. And finally, we write QED at the bottom to indicate that we are done. Let's now take a look at an example with a linear function, which is probably the easiest one to find the value for. Let's take a look at what it says. The limit as x approaches 5 of 4x minus 1 is 19. Let's identify the different pieces. The a value is 5. The function value is 4x minus 1, and L is 19. Now we're going to start on the scratch work side. This is going to be f of x minus L. So I write 4x minus 1 minus 19. My goal when I'm done is to have down here at the bottom absolute value of x minus 5 less than something. That's my goal. So I'm going to do whatever I can think of to try to get x minus 5 inside this absolute value? Well, the first thing I'm going to do is combine the -1 and -19 to get 4x minus 20. And then I notice if I factor out a 4, I would get an x minus 5. I factor out the 4 inside the absolute value, then I pull the 4 out. The absolute value of 4 is just 4, and then I need to divide both sides of the inequality by 4, which is positive, so I don't have to reverse the inequality. This tells me the absolute value of x minus 5 is less than epsilon over 4. That's what I was looking for. Now I'm ready to write the proof. Let f of x equal 4x minus 1, comma, and let epsilon be greater than 0. Choose 0 less than delta equal epsilon over 4, found over here, such that if 0 is less than x minus, write your a value here from the limit, less than delta, then start with your last statement, x minus 5 less than delta equal epsilon over 4. Then I divided by the 4, so I'm going to undo that by multiplying by 4. Then I'm going to pull the 4 inside the absolute value. Then I'm going to distribute it to get 4x minus 20. Then I'm going to split the minus 20 into 4x minus 1 minus 19. This is what I was trying to prove. And then we make the last formal statement. Thus, the limit as x approaches 5 of 4x minus 1 is 19, and we place QED at the bottom. What does this mean, actually? If I choose epsilon to be 1, then delta has to be 1/4. If I choose epsilon to be 1/2, then delta has to be 1/8. What I choose for epsilon is arbitrary, but the choice of delta depends upon epsilon. Let's now take a look at this one without all the sticky notes. This is what the final proof looks like when you do your work. Scratch work on the right, formal write-up of the proof on the left. You may want to pause the video and make sure you understand each step. Let's now move on to example 2, which will work together. In example 2, we're trying to prove that the limit as x approaches -1 of 4x plus 1 equals -3. Let's start by identifying our pieces. The value of a that x is getting close to is -1. My function is 4x plus 1. My limit value is -3. I'm going to start by writing 4x minus L inside absolute values. 4x plus 1, the function, minus -3. Don't mess up the signs. I want this to be less than epsilon no matter what I choose for epsilon. What's my goal? My goal is to get x minus a, or x minus a -1, less than something. So down here, I'm trying to get x minus -1 less than something. So my goal is to get an x minus -1 or x plus 1 inside these absolute values. First thing I'm going to do is rewrite the minus -3 as +3. Then I'm going to combine the 1 and the 3 into 4. Then I'm going to factor the 4 out of the binomial. And then I'm going to take it out of the absolute value. I guess I don't need parentheses anymore. I'm going to rewrite the x plus 1 as x minus 1. And then I'm going to divide both sides of this equation by 4. This is what I was after. When I choose epsilon, if I choose my delta to be smaller than epsilon over 4, or at most epsilon over 4, this should work. Now we're going to write up our formal proof. Let f of x equal 4x plus 1, and let epsilon be positive. Choose 0 less than delta equal to epsilon divided by 4, such that if 0 is less than x minus a negative 1 less than delta, then, and now I'm going to write this equation again, x minus negative 1 less than delta, and delta equals epsilon over 4, then I'm going to multiply both sides by 4, which does not reverse the sense of the inequality. Rewrite my minus negative 1 as plus 1. Next step, pull the 4 inside the absolute value. I'm going in total reverse to what I did on the right side. And then I'm going to distribute the 4. And then I'm going to get it in the form of f of x minus L. And my L was negative 3, so I need minus a negative 3. Now, how can I have what comes next? Minus a negative 3, in order to make it be, oops, I forgot my 4 here. In order to make it equivalent to this one, this has to be a plus 1. This is this step over here on the right. This is f of x minus, and this is L. And I've shown that the magnitude of the distance is less than epsilon. Then I finish with thus the limit as x approaches negative 1 of 4x plus 1 equals negative 3. And I write QED. Let's take a look now at the next example, which is another linear function. I want you to pause the video, work it out, and then turn the video back on and we'll compare our results. How'd you do? I know, it's complicated. Let's take a look at the pieces. A is 2, the function is 3x minus 2, L is 4. We're going to start with 3x minus 2 minus 4. We want to get x minus 2 less than something. The something will probably have epsilon. We start with 3x minus 2 minus 4, which we can rewrite as 3x minus 6. We note that we can factor out a 3, and if we factor out a 3, then we will get our x minus 2. We take the 3 out of the binomial and then out of the absolute value. We divide both sides by positive 3, and we get that delta should be no larger than epsilon over 3. Now we start the formal statement of the proof, and it does need to read pretty much exactly like this. Let f of x equal 3x minus 2, and let epsilon be greater than 0. Choose delta greater than 0 equal to epsilon over 3, such that if 0 is less than x minus 2, that's our a value, less than delta, then start with x minus 2 less than delta, which is epsilon over 3, then multiply both sides by the, then pull the 3 inside the absolute value, then distribute the 3, and then rewrite the minus 6 as minus 2 minus 4. The last thing you need to state is the statement of the limit again. The limit as x approaches 2 of 3x minus 2 equals 4, and you finish with QED. Let's now turn our attention to number 4. That's the solutions. I don't want to show you that yet. Okay, So we're going to work this one together. It actually turns out to be easier than the previous ones, but that's not always the case. This one, I think I'm looking at the wrong one. Example 4. There we go. This one is actually a quadratic, x minus 3 quantity squared. So again, we're going to identify our pieces. X is approaching 3, so a equals 3. Our function is the binomial squared, x minus 3. And our value of L is 0. Don't be thrown by 0. It's still a number. Now we start on the scratchwork side with the function value minus L inside absolute values. I have x minus 3 quantity squared, wrong symbol there, less than epsilon. That's what I want to prove, but I've got to work backwards to find delta to make it work. Now, what am I trying to get at the bottom? At the bottom, I'm trying to get 0 less than the absolute value of x minus a, which is 3, less than something. Well, this is awful close to that. The only thing that's missing is I've got this square, or rather it's present and needs to be missing. What do you think you're going to do? Yes, that's what you do. You're going to take the square root of both sides. You know they're going to be positive because one's absolute value and epsilon was chosen to be positive. So we end up with the absolute value of x minus 3 less than the square root. Oops, why am I writing a fraction? The square root of epsilon. Now we start writing up the formal proof. Let f of x equal x minus 3 quantity squared, and let epsilon be greater than 0. Choose 0 to be less than delta, which equals the square root of epsilon, such that if 0 is less than x minus 3, our a value, less than delta, then start with your absolute value of x minus 3 less than delta equal to the square root of epsilon, and then square both sides. And you get x minus 3 squared less than epsilon. Notice that we have an equals here, but a less than here. So the less than stays. And then we rewrite it with the L inside of it, which was 0. It sounds kind of silly, but that is an important part of the proof. This is what you're trying to show, that the absolute value of f of x minus L is less than epsilon. And that part you don't have to write in the proof. Then we restate the limit as x approaches 3 of x minus 3 quantity squared equals 0. And we write QED in the blank. Okay, I hope this is feeling maybe a little bit more comfortable. Let's move on now to example 5. In example 5, we're going to try another technique, which is to factor the numerator and denominator and try to get something to cancel. I'm going to pause the video. I want you to try this one on your own, even though it's a type you haven't seen, and see if you can figure it out. Then turn the video back on and we'll go through it. Our values for this one are a equals 3. The function is the rational function, x squared minus 9 divided by x minus 3. Our limit value L equals 6. We start by writing the function value minus 6. So we're going to start with x squared minus 9 divided by x minus 3 minus 6. Now you know that x minus 3 is a factor of x squared minus 9. What are we trying to get at the bottom? A was 3, so we're trying to get x minus 3 in absolute value less than something. In that sense, it may seem counterintuitive to cancel the x minus 3, but you have to take into account the minus 6. So we go ahead and factor x squared minus 9. We cancel the x minus 3 common factor, and that results in x plus 3 minus 6. And you're right, now it combines to give us x minus 3, which is what we were after. Notice we didn't have to do anything to both sides of the inequality. In other words, I can choose my delta to just be epsilon. Now I write up the formal statement of the proof. Let the function be the rational function x squared minus 9 divided by x minus 3, and let epsilon be greater than 0. Choose 0 less than delta equal to epsilon, such that if 0 is less than the absolute value of x minus 3 less than delta, then repeat the steps that you did on the scratchwork side, but in reverse order, ending with the representation of the function minus the L value. Finally, restate the limit that you were trying to prove and write QED. Let's now take a look at example number 6. Example 6 is similar to the one we just did. So again, I want you to pause the video, work it out, and then come back and we'll compare our answers. Okay, let's see how you did. This says the limit as x approaches 2, so the value of a is 2. We have another rational function, 2x squared minus 3x minus 2, all divided by x minus 2. My limit value L is 5. I'm going to start with the rational function minus 5. I'm hoping to end up with an x minus the a value, which is 2. The fact that this and this are the same, don't assume that that means anything. It's just happenstance. When we start with the rational function minus the limit value 5, we want to try to get rid of the fraction, which means if we can, we need to factor it. If it didn't factor and reduce, the next thing I would try would be a common denominator with the L value. In this case, it does factor, and the x minus 2 factor does cancel. That leaves us 2x plus 1 minus 5, and the 1 and minus 5 combine to be minus 4. Then I know I want x minus 2, and I have a common factor of 2, which I pull out of the absolute value, and I divide both sides by the 2. This gives me the absolute value of x minus 2 less than epsilon over 2. That's what I was trying to find. All of that is scratch work. I haven't done any of the proof yet. Now I start the proof. Let f of x equal that rational function, and let epsilon be greater than 0. Choose 0 less than delta equal to epsilon divided by 2, or something smaller, such that if 0 is less than x minus 2 less than delta, then, and now you write the steps that you followed on the scratchwork side in the reverse order, ending with the function minus the L value. Then you restate the limit and write QED. We want to now turn our attention to what I call more difficult proofs. I've gone ahead and written this one out for you because it is more difficult and rather challenging. I do not expect my students necessarily to be able to write one of these on an exam. I do expect that they could write the proof for any of the ones we've done previously, but 7 and 8 are rather challenging. I do think it's important that you see some of the ingenuity that went into solving these, and remember that these were not solved in an hour or a day or a week. It probably took quite some time for someone to come up with this method. In this particular problem, we have to impose an arbitrary limit on the value of delta. There's nothing algebraically we can do, to get x minus a trapped in the absolute value less than something related to epsilon without imposing an arbitrary value for a maximum of delta. We typically choose 1 to be our maximum value of delta, but that's also arbitrary. It's just our habit to choose 1. We want to do the limit as x approaches 4 of x squared, which we know, because it's a polynomial, is going to give us 16. But we want to prove that mathematically using the epsilon delta definition. We start on the scratch work side with the absolute value of the function minus L less than epsilon. This gives us absolute value of x squared minus 16 less than epsilon. Remember, my goal is to get an x minus 4 in absolute value less than something. I know if I factor x squared minus 16, it has a factor of x minus 4. So I'm going to go ahead and factor that difference of 2 squares. Now I need to isolate the absolute value of x minus 4 on the left, which means this x plus 4 factor must move. Now what I do is I take this and I split it now into the product of these two. Then I divide both sides of the inequality by the absolute value of x plus 4, forcing it, of course, to be positive. That way I don't have to reverse the inequality. The problem is that this representation also depends upon x, and that's not allowed. It has to be a constant with epsilon, or epsilon squared, or the square root of epsilon. Cannot have the variable x involved. So here's the technique that we use to get rid of the x on the right side. We arbitrarily choose a value for the maximum or minimum of delta, and we're going to choose 1. So we're going to take whichever one turns out to be smaller, 1 or whatever we find, which means that 1 is going to end up being sort of our maximum value. Then we say, okay, well, if delta is 1, how far away from A can I be? Remember that A is equal to 4. So if A is equal to 4, then I could be A plus 1, or I could be A minus 1. In other words, my x value has to be between 5, oops, can't get the eraser to work, and 3. All right. If x has to be 5 and 3, what does that tell me about the absolute value of x plus 4? Well, if x is between 3 and 5, I know I could add 4 to all 3 parts to get my x plus 4. So I add 4 to all 3 parts. And this gives me 7 less than x plus 4 less than 9. Note that 7 and 9 are positive, so x plus 4 must also be positive. I can replace it with absolute value then. It will mean the same thing because it's already positive. That means that I can write that this has to be between 4 and 9. And I should have put equal to or equal to. So I'll add that to each of my ones. It could be at the end point. So if delta is 1, it could be actually at 5 or at 3. Now the next part is super tricky. So let me write it out in a couple of steps. This actually means 2 statements. This means that 7 is less than equal to absolute value of x plus 4, and the absolute value of x plus 4 is less than equal to 9. We're going to look at each one individually. If I take the first one and I divide both sides by the factors that I have, In other words, switch sides with the factors. I know they're both positive. It won't reverse the inequality. That will put 1 over 7 on the right side, and it will put 1 over the absolute value of x plus 4 on the left side. What about this other statement here? And this would give me 1 over 9 here, less than equal to 1 over absolute value of x plus 4. Well, what does that mean? Well, it's kind of reversed things a little bit. What it means is that 1/9 is the smallest thing and 1/7 is the largest thing. I need to make sure that my value up here, where did it go, of my epsilon over x plus 4 is less than some number. So what I'm going to choose is this smallest value here of epsilon over 9. I'm going to choose this epsilon over 9 to fit here. Why? I know epsilon over magnitude x plus 4 is greater than or equal to that. And I know this epsilon over x plus 4 is strictly greater than my x minus 4 up here. Finally found it. So that means I can replace this epsilon over x plus 4 with epsilon over 9. I can't choose the upper end because that's too large. It's got to be the smaller one. Remember, for delta, we can always go smaller, but we can't go larger. Now we start at the top and we say, let f of x equal to x squared epsilon greater than 0. And you'll notice I've left some of the words out, which is okay as long as it reads mathematically like it would with the words in. Let delta be the smaller of 1 and epsilon over 9 greater than 0. So delta is less than equal to 1 and delta is less than equal to epsilon over 9. Then if x minus 4 is less than delta, which is less than equal to epsilon over 9, this makes x minus 4 absolute value strictly less than epsilon over 9. I know that epsilon over 9 is less than or equal to epsilon over x plus 4, which means that it has to be strictly greater than the absolute value of x minus 4. Now that we've gotten to this step, it gets easier. Multiply both sides by the factor x plus 4, combine them into the same absolute value, and then multiply them to get back the function minus 16. Therefore, the limit as x approaches 4 of x squared equals 16, and we write QED. Now, you may be wondering what this symbol is right here. It resembles a semicolon followed by a period. Sometimes you'll see it written more in a triangle shape. That symbol represents the word therefore. Anytime you write something a lot in mathematics, we tend to come up with an abbreviation or a symbol for it. So you start the final statement with a word like thus, hence, or therefore. And this symbol is the therefore. Let's now take a look at the next example, which is example number 7. Example 7 is the limit as x approaches 1 of x squared equal to 1. Which one was this? Okay. This is a more difficult one. Pause the video if you'd like to and work it out on your own, or you can wait and we'll do it together. Let's work through it together. Let's write out our values. A equals 1. The function is x squared, and the limit value L equals 1. We're going to start with the statement of the function minus 1 in absolute values. We get x squared minus 1 less than epsilon. That's what we're trying to prove. We want to end up with 0 less than x minus, what was our a value again? Oh yeah, 1. Less than something. Now, I know if I factor x squared minus 1, I can get an x minus 1 factor. However, it also introduces the x plus 1 factor, which I don't need on the left. So I divide both sides by it to get the magnitude of x minus 1 less than epsilon divided by the magnitude of x plus 1. And then I have to play a little trick. I'm going to choose, oops, lost my other O, delta to equal the minimum of 1 and something else. Now, it'll be the smaller of the two. I know that my A value is 1. So at a maximum, it's going to be 1 away. So A is 1, and A plus 1 would be 2, and A minus 1 would be 0. X has to be less than equal to 2, greater than equal to 0. Now I need to build the part that I need to get rid of, which is the absolute value of x plus 1. I need to build a plus 1 in here by adding 1 to all 3 parts of the compound inequality. Then, because all parts happen to be positive, I can replace the x plus 1 with the absolute value of x plus 1. Now, it is true that the absolute value of x plus 1 fits between did I add 1? I did not add 1 to that. I was looking at my number going, something's not right. Okay, so it is true that it has to fit between 3 and 1. But we need to find an even value on both sides. 1 is also greater than -3. So what we're going to do is we're going to put it between -3 and 3, or we could just leave it like this. Now, what we want to do, you could also leave it greater than equal to 1. And then we split it into the 2 parts like we did before. This means 1 over the absolute value of x plus 1 is less than equal to 1 over 1, and 1 over 3 is less than equal to 1 over the absolute value of x plus 1. And the one we want is the smallest, which is our 1/3. Since we have 1/3, we know that we can write x minus 1 less than epsilon over magnitude x plus 1, which is less than equal to epsilon over 3, because the magnitude of x plus 1 is less than 1/3. This means that I can write x minus 1 less than epsilon over 3. And that's what I was looking for. Now I start the formal side of the proof. Coming up here, I let my function be represented by x squared and epsilon greater than 0. I choose delta greater than 0 to be the smaller value between 1 and epsilon divided by 3. And we write sets in curly brackets, such that if 0 is less than x minus the a value, which was 1, less than delta, then, and we start again with the bottom statement on our scratchwork side, which is x minus 1 less than delta, which is less than or equal to epsilon over 3. Remember that we chose the smaller, so it's the smaller of the two. Now, the next thing that we're going to write after we've written that part is we move up to the previous statement. So the previous statement had this in it right here. We know this is less than equal to 3, but we know that this epsilon over 3 is greater than epsilon over x plus 1. So now we can write x minus 1 less than delta, which is less than equal to epsilon over x plus 1 less than equal to epsilon over 3. And now the next thing we do, of course, is multiply both sides by the x plus 1. And this means it is strictly less than epsilon. Then we multiply that out to get x squared minus 1 less than epsilon. This actually is what we were looking for, the function minus the limit value. So we're done with that part. We come to the bottom, we rewrite the statement of the limit, which I'll write here. Thus, the limit as x approaches 1 of x squared equals 1. Thus, hence, therefore, whichever you prefer, QED. All right, let's take a look now at the next problem, which is another challenging one. This one requires a slightly different technique, not the same technique that we used before. I think actually this one is somewhat easier to my mind than the one we did previously. Let's go ahead and identify the parts of our proof. A is equal to 9. The function value is equal to the square root of x, and the limit value is equal to 3. We start, as we always do, with the function value minus the limit in absolute value. Square root of x minus 3 less than some epsilon. Now, what are we trying to get at the bottom? We need x minus a, or x minus 9, in absolute values. And it needs to be less than something. Now, when I'm looking at this one up above, and I'm trying to visualize how on earth am I going to get an x minus 9, nothing comes to mind at first. And then I look at the square root and I think, well, if I multiplied by the conjugate, I could get x minus 9. That means if I multiply by the square root of x plus 3, I could get my x minus 9. But I'm not allowed to just put that into the equation. So I'm going to have to write it as a form of 1. The square root of x minus 3 over 1 times the square root of x plus 3 over itself. Now I multiply together the numerator with the difference of two squares pattern, the conjugate pattern, and I get my x minus 9. But unfortunately, I have this square root of x plus 3, which I don't need on the left. Oops. So what am I going to do? I could try doing that minimum trick that I did before. But if we think about this, we may be able to work it out a little bit simpler. What is this going to be less than? What will make this fraction as large as it possibly can be? Well, to make a fraction larger, what do you need to do? You either need to make the numerator larger or make the denominator smaller. It's the denominator I need to get rid of. And what would make this as small as possible? Well, the smallest possible value I could put in the denominator is 0. And that would give me a 3. So I know that this x minus 9 divided by the square root of x plus 3 must be less than or equal to this largest possible value for it, which is x minus 9 divided by 3. To make the fraction as large as possible, I made the denominator as small as possible. If this is bigger than that, and I want both of them to be less than epsilon, could I then multiply both sides by the 3? And the answer is yes. This gives me x minus 9 less than delta, which is epsilon divided, or not divided by, multiplied by 3. This is kind of a strange one in that my delta is larger in value than my epsilon, but it works. All right, let's go ahead and write up the formal side of the proof. Let my function f of x be the square root of x, and let epsilon be greater than 0. Choose 0 less than delta equal to 3 epsilon, such that if 0 is less than the magnitude of x minus 9 less than delta, that's my a value, then, and we start again at the bottom, x minus 9 in absolute values less than 3 epsilon, which means that x minus 9 divided by 3 is less than epsilon. But I know that x minus 9 divided by the square root of x plus 3 is less than the absolute value of x minus 9 divided by 3, and it's less than epsilon, then I can state that the magnitude of x minus 9 over radical x plus 3 is less than epsilon, which puts me at this step here. And I break it apart by factoring the x minus 9 into square root x minus 3 and square root x plus 3. I don't know if you knew you can do that, but you absolutely can. So this then becomes the square root of x minus 3 over 1 times the square root of x plus 3 over the square root of x plus 3, which is less than epsilon. Then we can take out the 1 part and just end up with the square root of x minus 3, which is our function value minus the limit. That's what we were trying to prove, and that means that we're now done. Then we restate the value of the limit. Thus, the limit as x approaches 9 of the square root of x equals 3, and we write QED at the bottom. Okay, I'm sure you are exhausted. The epsilon delta definition of the limit is so complicated and so difficult that it really tires the brain out. So let's take a break. I'll end this video here, and in the next much shorter video, we'll just take a look at what it means to prove one of the limit laws using the definition, and also we'll take a look at the definitions for a one-sided limit and infinite limits. Right now, you need a break. Go and do something else and come back when you're feeling fresh to finish the small, tiny bit we have left on the epsilon delta proof.